Hello and welcome to Fun with Physics with Uncle Bob. This week we'll be looking at the traveling salesman problem using a technique that I developed that gives near optimum multiple paths as output to the program. This program is simple and fast. The one thing I do want to say is I did not do a complete literature search on this, so others may have developed similar techniques. Anyway, this program starts by finding the closest neighbor given a set number of points or cities to visit. Then the program will randomly pick from 3 correction algorithms I developed and apply those in a successive approximation technique, giving an output of multiple paths that are either optimal or near optimal for you to choose from. These are the 3 correction to path algorithms I'll be using and talking about. 2 will be shown on the upper path, 1 on the lower path. The points are labeled in order here. Note that the solid lines will be the original path. The corrected path is shown by dotted lines here. So I'll go through the first path correction algorithm with you. What happens is we notice that point 4 between 3 and 5 in our original path is not optimal. It would be much better placed between these points 10 and 11. So this would be indicated by taking out point 4, going between 3 and 5 in our original path, replacing it with a path going from 3 to 5, inserting point 4 between our points 10 and 11 here. Note that this repositioning of this point 4 occurs in this instance later in the path. We can also have the situation where we're coming around and we notice a point 4 coming down here where the point 4 occurs earlier in the path. Those are the 2 correction algorithms for a point that is just out of place but not crossing as shown down here. We'll go down here where we have another situation where we got crossing paths, which is rarely optimal. It's much better to go on the dotted lines here, here, and here, here, and take out this path here. So those are the correction algorithms we'll be doing. Let's take a look at an output and also the program software itself. This is my program written in Power Basic. I like Power Basic because it's fast and stable. Anyway, we're starting at the top, and of note here would be user input in this section here. The number of trials I've got set equal to 10. That will be the number of near optimum paths that it will display in the output. Because it's a randomized process, some of these 10 may be duplicates and some not. It's different every time. You just run it and see. N equal 80, the number of points or cities to visit. Runtime I've got equal to 1 second. This is the time to run the main computation for each of these 10 trials. This program runs very fast, typically is done for each one of these trials in less than 0.4 seconds. Xmax is specific to my display, so yours may be different. This is just on the graph output that you'll be seeing, the plot scaling factor and the graph size here. Feel free to pause and study or copy this as you wish. I'm going to move the program or paper up so you can get a better view of more of it. Feel free to pause. Go up again. That's page 1. We'll go on to page 2 here. I'll move up. And up again. And finish page 2. Nearly finished. I'll go on to page 3. Here we have most of the rest of this is data points, as you see. I'll go on up. And to finish up the data, end of programs right here, page 4. And that's it. Let's look at some output. I'll go ahead and run that program now. You'll see on a display output occurring very quickly a sequence of various paths. The first path being the nearest neighbor approximation to start with. Run. Here it comes, our nearest neighbor. It will find better paths. It will be doing 10, some of which may be duplicates, so you may not see 10 different shapes here. We'll see when it gets finished in a few seconds. The last path displayed will be the best path it found out of those 10. So you can always bring this back up. This will remain stable. It looks like it's stable now. I'll minimize it. Look at our numerical output right here. And I'll bring it up. Notice that your 10 paths are here. The best path it found was a length of 647, which occurred here and here, so twice. And then we've got duplicates here of 651 and also 652. If you wanted to look at these paths of 651 or 652, you come over and rerun your program with num trials equal to 1 and run it a few times, and these will recur. You can look at that path output display when you run it one at a time and take your time. It will list the sequence of cities or points to visit here, but when you run it multiple times, it simply finds the best path and the sequence of cities or points to visit, given a left to right, and then on down to the next row, left to right. So we found 647. Here it is. You can also bring that path visual display back up. It's the last one saved. Again, when you run multiple paths, it always saves the best path it found, and you will see that here. You can look at it at your leisure. So there you go. We'll see you next time on Fun with Physics with Uncle Bob.